Today, in an attempt to move towards solving finite games in general, we're going to start to talk about equalizing strategies and move forward from there. We'll begin by reminding ourselves of what it means to say we have an optimal strategy for an m by n matrix game, with the matrix here given by matrix A. So remember, as always, we have two players, player one who picks a row, player two picks a column, and the entries here of the matrix, the a sub ij, that's the entry in the ith row and jth column, will represent the payment from player two to player one. We'll talk about optimal strategies, and here let me make a quick comment on notation. I think in the previous video lecture I used the strategies as column vectors. In our author in our textbook has switched from some versions to other versions, from having row vectors to column vectors. I think in the PDF version that most people have uses row vectors, so I'm going to be using row vectors to indicate strategies. In this case, for player one, I'll have the vector P with entries P1, P2 up to Pm, representing the probabilities that player one plays row one, row two through row M, and Q equals Q1 through Q, that should be Qn. The probabilities that player two plays column one, column two through column n. And remember, since these are probability vectors, we need to have P1 plus P2 up to Pm equal 1, or in other words, the sum from, we'll be using this notation, I equals 1 to m of P sub I equal to 1. And similarly for Q, the sum from j equals 1 to n of Q sub j must be 1. The value of the game V, we've seen before, is characterized by these inequalities. It says the sum from I equals 1 to m of P sub I times aij must always be greater than or equal to V for each j equals 1 to n. How do we interpret this? 2 is playing column j. We can just go to the jth column here. If j equals 3, the expected return would be P1 times A13 plus P2 times A23 up to Pm times AM3. That's exactly what we would have here. And this says that for every choice of column, for every j equals 1 through n, the expected return for player 1 is at least V, the value of the game. In other words, player 1, no matter what player 2 does, player 1 gets an expected return that's at least as good as the value of the game V. And similarly, this quantity on the left represents the expected return this is the expected return if player 1 plays row I. So if player 1 plays row I, that would be A I1, AI2, etc. The expected return would be Q1 times AI1 plus Q2 times AI2, etc., all the way up to QM, no, Q sub n times AIN. That would be this quantity on the left. And this statement that this is always less than or equal to V for each choice of I equals 1 to m says whichever row player 1 plays, if player 2 is playing the optimal strategy Q, then player 2 does no worse than V, gets a return that's less than or equal to V. That's better for player 2, at least, than V. Now, let's take a look at what happens when both players play optimal strategies. Well, we're going to write down a big string of equalities and inequalities, and we'll see that something nice happens. The value of the game V can be written like this. Why? That's because the sum from j equals 1 to n of Q sub j is just 1. We're just sticking a V times this quantity 1 here. But now, remember, we had above that V was less than or equal to this quantity. This was exactly that expected return if player 2, if player 1 plays the optimal strategy vector P, and player 2 picks column J. So this quantity is always greater than or equal to V, so we get this inequality here. Now we're going to translate this sum of these sums into a double sum, I equals 1 to m, j equals 1 to n, of p sub I aij times qj. That just says for every choice of I from 1 to m and every choice of j from 1 to n, we get a term that looks like this times this. Writing it as a double sum, that just means we're summing over all possible pairs I and j, this quantity here. Now, this thing here represents something very simple in the matrix. What does it represent? Well, it says look at every entry of the matrix, all possible I and j, I going from 1 to m and j going from 1 to n. And let's say here in the middle you have somewhere aij in row I, column j. We're multiplying aij by p sub I and q sub j. P sub I is the probability that player 1 plays row I, and q sub j is the probability that player 2 plays column j. So p sub I times q sub j is the probability that both of those things happen. In other words, the probability that when both players are playing these optimal strategies, that we end up exactly here in the matrix and get a return aij. So this return aij happens with probability p sub I times q sub j. So what happens when we sum up over every entry in the matrix? P sub I times q sub j, that's the probability of landing there, times aij, the payout in that situation. We just get the expected return when both players play their optimal strategies. So this is exactly the expected return when both players play the optimal strategies. The vector P and the vector Q. This is the vector P for player 1 and the vector Q for player 2. This is adding up all m times m possibilities of what can happen with the appropriate probabilities. And then we just kind of decouple them again by taking them out in a different order. We'll write the sum from I equals 1 to m of p sub I times the sum from j equals 1 to n of a sub I j q sub j. You can see that this sum of the sums, again, for every single value of I and j, gives you exactly the same quantity, p sub I times aij times q sub j. So this sum has to be the same as this other double sum. And that will be less than or equal to v, because we already saw that this quantity here on the previous slide, this quantity here is less than or equal to v, because this quantity represents the expected payout if player 2 is playing the optimal strategy Q and player 1 plays, in this case, rho sub I. And we saw that in every case, if player 2 is playing an optimal strategy Q, that this will be less than or equal to the value of the game V, because with an optimal strategy, player 2 always does at least as well as V, which here means less than or equal to V, and because the sum of the p sub i's is 1 when we're multiplying each time by something less than or equal to V, the whole thing is less than or equal to the value of the game V. Now, when we put all of these inequalities and equalities together, we have V on the left is less than or equal to, and again, less than or equal to V on the right. The V, of course, is equal to V. The left side here is equal to the right side. The only way these two things could be equal is if every term were equal. If any one of these inequalities, this one or this one, were a strict inequality, there's no way that V could equal V. And of course, that would be a contradiction since V does equal V. So what does that tell us? It tells us we have equalities here and here. And then all of these are each and every entry here is equal to V. In particular, this quantity here, this expected return when both players play optimally, is exactly V, the value of the game. That's not surprising, but it's a nice thing to see formally as we've seen it here. Now, we've learned to solve many games, especially 2x2 games in the past. And we've seen that often equalizing strategies are optimal strategies. So again, I'm repeating here the characterization. We've seen this several times. If player 1 plays strategy, mixed strategy given by the vector P, P1 through Pm, and again I wrote this wrong, that should be player 2 plays Q, which is Q1 through Qn, then these inequalities must hold. But when we're looking for equalities, we try to solve the equations when we put equalities here and here. Let's look under what situations we've already seen where this works or wouldn't work. We've seen for 2x2 matrix games that one of two situations must occur. Either the 2x2 matrix game has a saddle point. You'll see in this second example, this 2x2 matrix 1, 4, 2, 9 has a saddle point. The number 2 is the smallest number in its row and the largest number in its column. So we know what an optimal strategy is. Player 1 plays row 2, and player 2 plays column 1. In other words, our optimal vector P is just 0, 2. It's a pure strategy. I'm sorry, 0, 1, I should say, playing row 1 with probability 0, row 2 with probability 1. And our optimal strategy Q for player 2 is 1, 0, playing column 1 with probability 1 and column 2 with probability 0. And it's clear that when both players play this, the value of the game is exactly 2. Each player can assure himself, in fact, both players will always get a payout of have a payout of exactly 2. Remember, that's 2 from player 2 to player 1. Neither player can do better with a mixed strategy. And you notice these are not equalizing strategies. Player 1 doesn't do just as well. If player 1 plays this optimal strategy, always picking column 2, player 1 does not do equally well, regardless of player 2's choice. Player 1 can guarantee at least this value 2, the value of the game, but player 1 would just love player 2 to play column 2, then player 1 gets 9 instead. Similarly, player 2 plays column 1, is guaranteed no worse than a payout of 2, but again, it's not an equalizing strategy. If player 1 switches and picks row 1, player 2 is better off, only has to pay out 1 in that situation. So when there's a saddle point, equalizing strategies are not possible, and the optimal strategies with the saddle point are these pure strategies that lead to the saddle point. Now, in this first example here, we have a 2x2 matrix game where there is no saddle point. And what we learned is when there is no saddle point, in fact, then optimal strategies are equalizing strategies. We learned to compute those in the general case where you have A, B, C, D here, arbitrary numbers, in this situation when there's no saddle point, and we derived formulas for exactly what the value of the game is and what the optimal strategies for player 1 and player 2 are, and those optimal strategies were the ones derived from equalizing strategies. So we use equalizing strategies here, we can't use them here. Is there some way to understand in a more general way when we can use equalizing strategies to get optimal strategies? And the answer in the general situation is that can be very tricky. But there's a lot we can say.